Thank you for saving me sometimes. Yeah. So I'm Hung, a Ph.D. student in deep learning, and my research is about computer vision and video understanding, and recently large language model. So it's great to be here today to start the new meetup of the year with like some talk about LLMs. And for your information, this background is generated using Microsoft DOI. So yeah. So so today we will talk about training and inferencing with large GPUs. So last year was actually a year of AI, where like everybody was crazy about this AI and particularly large language model. And people start talking about LLMs, using LLM in their work, and some people also want to use open source model for their business. But at the same time, the cost of training and inferencing using these techniques increased very significantly. And for the reference, so I checked today's price of Lambda, the cloud for GPUs. So the price for renting a A100, the machine for using this model, like it is from $1 to $5 an hour. So imagine you want to serve this model like 24 by 7. It can be a lot of money. So it's best to learn how to use these techniques efficiently and effectively before using this model. Otherwise, you will burn your money. So today, I'll talk about two things: how to do inference with large GPUs. So I'll cover like model partitioning, model quantization, and some demo on how to inference on CPU. And then I'll talk about how to train with less GPUs, but I will cover the difference between like full file tuning with like LoRA and prompt tuning, and cover like Zero, a very good framework for training big models, and LoRA, and I will show a recent development of like Microsoft and other big techs in using smaller models. So let's start with the first part, inferencing with less GPU. So before I dive into the details, I think it's better to understand the problem that before trying to propose a solution, it's better to understand the problem. So to understand the problem of large model, we need to first look at how things work inside a GPU. So initially, your machine have a disk, a RAM, and a GPU. So when you download the model from the internet and the data from the internet, they will be stored on the disk. When you start your applications, the Python applications, this thing will be read and put into CPU RAM. And when you call like touch.cuda, everything will be moved into GPU, and the computation will be done on GPU. For the computation to be done, the size of the model and the size of the data need to be fitted within the GPU's capacity. And that's where we have problem with large models, because these are just too big to be fit inside one GPU. So for example, Llama 7B, a famous one, has a size up to 28 gigabytes, whereas Llama 33B, it has a size of like 132 gigabytes. By comparison, we have a free collab GPUs, only have 15 gig of RAM. Even we have the A100 series only have 80 gigabytes of RAM. So we cannot fit the Llama 7B to a single A100 GPUs. So the techniques I introduced aim to reduce the size, the memory usage within each GPU. So we can do that via model partitioning and quantization. So for model partitioning, the idea is like pretty simple. So instead of fitting the whole GPU, the whole model to the GPU, you instead partition the model into several parts. And each time you load each part of the model to the GPU and the data, you perform computation with that part, and then you free the GPUs, and then you load the next part to the GPU and perform the next computation. You do that sequentially until you reach the final result. For multiple GPUs, you do the same thing. Now you have multiple parts of the model at different GPUs, and you load the data to each part of the model to perform computation. So these techniques allow you to run any model. So in theory, it can allow you to run any model on any small GPUs. So you just need to partition the model to be small enough to be fitted inside your GPU. But it comes with cost, because the more you partition the model, the more you need to move the data and the model around, and that can significantly increase the inference time. And so you are like basically trading off the speed with the runnability. So you can do that like by default by hugging face. So that is the link if you want to have more details. So that's one way to reduce the memory usage inside one GPU. The next way is via quantization. So with quantization, you do that directly. So from the Llama 7B, with 8-bit quantization, you can reduce the size of the model to 7 GB. And if you want to go further with 4-bit quantization, you can reduce the size to 3.5 GB. These are really small and can be fit to even your local GPU. But what is quantization? Actually, what is quantization? So to understand model quantization, we need to understand how deep learning models are represented in computers. So they are just a bunch of matrices, and each element in the matrix are floating point numbers. So PyTorch and TensorFlow and deep learning frameworks, they represent each float number using 32 bits. And with quantization, you represent those numbers using less bits. So 8-bit quantization, you represent the data using 8-bit. With 4 bits, you represent the data using 4 bits. And because we represent the number using less bits, we significantly reduce the size of the model. So if we move from 72-bit model to 8-bit, we reduce the size 4 times. And note that, so with like 8-bit quantization, we can fit everything to a single free collab GPUs. And that is amazing. So I will give you some demo. Here. So here is the Google Colab, free version of Google Colab. And if I load if I read the Llama 7B, it will result in like the system crashed because there's not enough memory to load everything to read. There's not enough memory to load the model. But if I read the model and I quantize the model, the size of the model you can see is reduced from 28 GB to 7 GB. And now we can do some like inference with Llama 7B on a free GPU, costing no money. So apart from being able to run bigger model in smaller machine, quantization also allows us to run the model in less amount of time. Because the size of the model is smaller, we can achieve incredible speed. So for some research do like quantize this 175 billion model, and they reported that they can run it on one single A100 GPU with the speed of 10 tokens per second. Now that this is the size of the ChatGPT. So basically they can run the whole ChatGPT model in one GPU with decent speed via quantization. So quantization seems too good to be true, right? But that's come with some cost because now we are representing the float number using less bit. It's significantly changed how changed the number. So you can see, like originally, we represent the number using 32 bits. So it's like normal float. If we represent the same data using 8-bit, it will turn into integer. And remember that large language model is a generative model. So a small change in the model and the data can lead to a huge change in the output. Here's some demo again. So thanks Microsoft for having this like file model. So it's very like lightweight. So the original model take 11 gig of RAM and GPUs, and the quantized model takes like one quarter less than that. So I can load everything to a one free GPU of Google Colab. And at first, the response of the two models are similar, but they start to diverge like at the second sentence. So the original model say that Melbourne has rich history, diverse culture, and beautiful landmarks. And the quantized model agree with the first two, but like start like diverse. It say that okay, our city has some vibrant art scene, and the response from there become very different. So some research quantize, so they measure how difference is, so the difference between the quantized model and the original model, and they conclude that the quantized model is less accurate, but the difference is negligible, as you can see on the chart. And the surprising thing is that, so if you quantize a larger model, the gap between the quantized one and the original one is like almost nothing. So to recap, so this quantization can significantly reduce the memory usage, allow us to run bigger model on some small machines like Google Colab, and can reduce the inference time. But we are sacrificing some of the model accuracy. And you can do that. So if you want to use these techniques, so if you want to use 8-bit quantization, Hugging Face allow you to do so by default, out of the box. But if you want to do like more than 4-bit quantization, now we are representing 32-bit number using only 4 bits. So we need some special techniques to ensure the accuracy of the model. So there's some dedicated libraries for that. So you can check the link I put here. So the techniques I show so far is for inference on a single GPU. But what if we want to do inference on edge devices? So normally we do that by let the edge device stream in the input to the server, and let the server do the computation and stream back the output to the edge device, like what Andy usually do here. But what if we want to do inference on the edge device itself? So actually we can do that. And via some brilliant engineering tricks in Llama CPP here, we can do inference on CPU, and they can support very fast inferencing on Mac, and support running on Android phones. So here's the last demo in my talk. So I run some 7B model on my laptop. My laptop is a ThinkPad model, so it's a very normal one, no GPU, Core i5, and 8 GB of RAMs. And I will ask it about our Melbourne city. So you can see the speed is very decent, and the response is, I think, it's good enough for me. So for comparison, so here is the response and the time, the speed, if I ask ChatGPT. Melbourne is. So the speed is, you say, it's almost, definitely not much with ChatGPT, but it's almost there. Even that we are using a open source model on our machine, we don't need to care about data privacy, and this is definitely worth a try. So that is for inferencing on CPU. So to recap this session, so we have talked about how the problems of large language model when we do inferencing, they are just too large to fit inside GPU, and we solved that problem by first by partitioning the model, allow only a small part of the model to be fit into the GPU at a time, but that trade off speed with runnability. And the other technique is quantization, where we represent float numbers using less bits, and it can achieve significant memory reduction, but we need to trade off some accuracy. And there's someone that I want to mention, but briefly mention, but not talk into detail, is some advanced techniques for those who want to use LLMs as a service, serving multiple users. So for serving multiple users, you need to take into account so you need to serve multiple users at once. So you need to ensure the short amount of response for all users. So you need to do batching. You need to do parallel processing of multiple users at once. So dynamic batching is a technique that allows you to reduce the memory further when you do that, when you serve multiple prompts at once. And it can achieve very significant throughput reduction. But I won't dive into details in this talk. The other one I want to mention is speculative decoding. And this decoding is very clever, and it's a clever way to do decoding. It uses some smaller model to improve the speed of the larger model and achieve 2 to 3 times acceleration time. So if you're keen, I put some link on the slide for further reference. Now, we talk about training with less GPUs. So before diving into it, so I want to have some distinction, to show some distinction between full fine tuning and other fine tuning techniques that we see last year. So full fine tuning is the traditional way we do when we want to fine tune deep learning models. We basically update the whole models using gradients, and it usually requires lots of data. And if we want to fine tune large models, it can take months or weeks. But because we change the whole model, the resulting model is very different from the original one. And analogous to that, it's similar to how we update the whole operating system. So the designing of the new system it takes a long time, and so the new system is completely different from the previous systems. By contrast, LoRA adapters and prompt tunings, these just changed a small part of the model. But because they only change a small part of the model, they require very little GPUs and only require a few amount of data for the fine tuning. It can be done in a few hours, but the fine tune the resulting model is not very different from the original one. So it's like how you update your Windows. So you update your Windows, it takes you a few hours, but the results, after update, you won't notice any difference. So this is somewhat similar. So if you want to train the model, so there's some bad news, because you need significantly more GPUs. So instead of just having the model and the data, now you need to have the gradient and the optimizer to be fitted inside a GPU. So a small quiz, the model weight, the gradient, the optimizer, and the data, which of the one will take the most GPUs, given batch size of 1? Anyone? Optimizer? Yeah, correct. Okay. So given the size of the model, like if the model had the size of 3 gigabytes, the optimizer takes 8 times more memory. So it takes 24 gigabytes of memory. So the total, if we have the machine to run the Lambda 7B, it will only be able to train the GPT-2 model. So, and the more memory consumption is scaled with the number of training parameters. So the idea here is to try to reduce the number of training parameters to make it manageable within 1 GPU.
Is there a recommendation of having GPU versus RAM? Like how much RAM should be there? If we are partitioning to level X, then the RAM has to be this much of GPU.
So if you don't have enough RAM, you have option to let the model sit inside the disk. You don't need to load it. You only need to load it when you need it.
Then the performance will go even
slower. Right? Yeah. So the more you move things around, the slower the speed.
Understood if the memory is low, understand. Then if the page file or something such can take off. But the question is there a recommendation of how much RAM should be there?
How much RAM should we prepare?
If the partitioning is on 8-bit, then the RAM has to be this much of GPU. If I
Yeah, normally, in cloud machines, I don't know, like in cloud machines, the RAM is not the problem. The RAM usually we have like lots of RAM. We have in our lab machine we have 1 TB of RAM. So, but normally, if you if you can get the RAM equal to the number of GPUs, it's good. But if you don't have, so there is something called offloading. So normally you load things to RAM before you load to GPU, right? Now you don't need to load it to RAM. You need to let the model part sit on the disk. So when you need to load that model part, you start read the model part from the disk, load from the RAM, load to the RAM, and from the RAM to the GPU. So you don't need to read the whole model before doing partitioning. You do partitioning before doing inference. So if you look at Hugging Face side, you could see that they don't put the whole model as one single file, but they split the file into multiple parts. That is for like offloading when you want to have like every part of the model sit inside the disk. So do you get what I mean?
I get it.
Okay. So here is the paper that allow you to do partitioning for training. So like the title says itself, so it allow you to partition not only the model, but also the optimizer and the gradient. But the good thing of this zero framework is that so they allow us to do like very significant memory reduction, but with only a few percent slower, like a few percentage slower. So like we can achieve like 64 memory reduction with only 1.5 times slower. So like training like 7B model can take 120 gig, whereas if we can partition it to like 64 in this experiment, we can reduce it to 64 times. And if you don't want to partition everything, the parameter, the gradient, and the optimizers, you can choose some options to only partition the most like the most memory hungry one, the optimizer, and they reported to achieve 4-time memory reduction with same training speed. So we get 4-time memory reduction without sacrificing anything. So that is the cool thing about this this techniques. I think it's from Microsoft. So this is for partitioning the model. So they don't do anything to reduce the size of the training parameters. So with LoRa's, we actually like try to make the training manageable by reducing the number of training parameters. They do that by keeping the model the same. They don't touch the model during the training, but they train a separate part, like the orange part here, and they keep this part manageable. So later on, they will add this part to the model to update the model weight and change the model behavior. So if they don't want this part anymore, they can just subtract the model with this trainable weight to recover the same model, the previous model. So it's like similar like how we using Windows patch to update our Windows. So what does it give us? So because we only train a small part of the model, the number of training parameters decrease significantly. So and the result is the same. So it's cool. And not only that, so because we only train a few parameters, we only need a few data compared to full fine tuning. So in this experiment, they reported to have like 90% accuracy using only 300,000 samples compared to full fine tuning. It's even better than full fine tuning. So because if we want to fine tune the whole model, we need to have, because the model has a lot of parameters, in this case 175 billion, we will need a lot of data. But with LoRa, we only need to train a few thousand or millions, so 300,000 is enough. So there's some blogs that report that they compare the memory usage between LoRa and full fine tuning. So with like LoRa, they can train the Llama 7B using only 1 GPU. Whereas if we want to do full fine tuning, we will need like 2 GPUs of 30 gigabytes each. And the training time you can do, if we use LoRA, you can train it in under more than under 4 hours. But with fine tuning, usually full fine tuning, usually we need like days or even weeks. So those are the benefits of LoRA. But there's something to consider. Like firstly, so the pros is there. It can reduce the training parameters and faster train and require less data. But from my observation, so for LoRA to work, the fine-tuning task needs to be similar to the pre-trained task and also the data. So it will be suitable when you have a pre-trained model, obviously. And the pre-trained task needs to be similar to the fine-tuned task. For example, if you want to have a model, you want it to behave in a certain way, more safety and like less toxic, you will do LoRA. But it will not suitable when you want something like totally different from the original model. Like you want to use Llama B for like material science generation, it's not gonna work. So yeah, that is a limitation of LoRA. So like recently, there is a development of using smaller models. So instead of fine-tuning the very big models, which can take days or lots of GPUs, it's actually that we can train very small model, like 1.3 billion, and still achieve good results. The key thing here, there are two key things for this to work. First, we need to choose a specific task, because small model cannot generalize well. And the second key thing is to have high quality data. So this is from textbook, is a unique paper from Microsoft that the report so by careful curation, data curation, their model can achieve better performance at code generation compared to other like 10 times bigger models. So this development is amazing because it tells us that, so instead of like spending money to scaling machines or developing bigger models, we just be more careful about our data and we can still get good results. So that concludes my talk. So anyone have questions?
Got a good amount of time for questions. So who'd like to kick us off? Patrick?
Yeah. So if you're an idiot like me who wants to use LoRA, I know with conventional fine tuning, I can just download the model and run model.fit. Is there like a model.LoRA fit for if I want to do the same thing with LoRA, or do I have to kind of roll my own?
So there are some. So it's not supported by default in PyTorch yet, but there's some like very good GitHub repo for you to just clone their code, replace your model with their model with your model, and just run their code.
Down the back.
I wanted to ask you about something that is not this latest, but neural architecture search.
Neural architecture search, okay.
This model, and you would like to kind of search for the exact weights and the parameters to improve the inference latency and also reduce the model size.
Mm-hmm.
Neural architecture search.
Yep.
Does LoRA and Zero come under something like that?
Uh,
Are you searching for something over here, like optimizing a problem?
Let me think.
Searching for like a weight adjustment
Yeah.
with LoRa architecture.
Hmm.
Yeah, you're not searching for architecture, you're just adjusting the weights and biases a bit.
So LoRA is a bit different. So neural architecture search, what I remember is that it tries to find the set of architecture that can best fit the problem, right? But LoRA is just like it's similar to full fine-tuning, but instead of fine-tune the whole model, it learn the set up small weight and add to the model. So LoRA is similar to full fine-tuning, but more efficient, whereas neural architecture such is a whole different story and can take very significantly a lot more time to do, right? So yeah, for more details, I am not very.
LoRA is more about the matrix properties, right? Because all these things are matrices. So it's random decomposition mainly that's happening. So you're not basically doing much with the architecture.
Yeah, we don't care about we keep the architecture the same in LoRA. So it's like full fine-tuning.
Can I ask something?
Yeah.
When you have all these when you split the partition the model in on certain GPUs,
Mm-hmm.
and during training, and then you basically are training and you optimizer, you also split the optimizer, you still need to communicate to update the weights. You can't update the state of the model uh, by partitioning unless all the parts talk to each other. So how does that communication get optimized?
Yeah, great question. So like partitioning does not mean parallelism, so it still do that sequentially. So normally when you do inference in the model, like or training in the model, you will like the output of the first layer is this input of the second layers. So you still do the same in model partitioning. So when you reach the end of the last layer of the model, you will start doing like parameter gradient updating. So it's different from their data parallel. So in data parallel, you have multiple models duplicated across multiple GPUs, and then you have the data split into multiple GPUs. Each model at each GPU will compute the loss, and then you aggregate the loss, and then you will do gradient updating. Here, model partitioning is different, although you split the model across multiple GPUs, but you still do need to do it sequentially.
And does that depend like how faster the sequential is it controlled, like the band? Because suppose it's a bandwidth or something, how they're communicating with each other. Like, are there techniques to improvise that?
So communicate with each other. So you mean you want to you have a distributed system?
Yeah, in a sequence, because and also, so you mean like when it's sequential update, so till the next part is doing its job, the first part just rests empty, like it's not doing anything?
Yeah.
Yeah.
So because it's sequentially, because it is a sequence, it still do it sequentially. So
Got a dumb question.
Yep.
Suppose I do have like one GPU.
Yep.
And I did partition of smaller bits on the model and trained it. Now when I want to validate or I want to use it, I want to use more GPUs. So I increase the bit size and try validating and then using it. Will it reduce? Will it provide me the same output it provided in less GPU, or the output would be different?
So great question. So are you mentioning you are doing quantization or are you doing partitioning?
Both.
So with quantization, so the technique I mentioned is post-training quantization. It means that you already trained the model. It's like full bit size, so it has 32 bits, and then you want to compress it for later use. So you don't train the model again. You just need to do like quantization on the already fine-tuned model to get the smaller model for inference. So if you want to do fine-tuning, LoRA fine-tuning on the quantized model, there is actually a recent method that allows you to do that. It's called QLoRA. So the idea is to dequantize so it has the 4-bit quantized model. So it first dequantize the model to be from 4-bit to 16-bit, and then train the LoRA layer on the 16-bit, and then we get a 16-bit model. But it's not guaranteed to have the same performance with the original model because the act of like dequantize is a lossy operation. So there's still some difference in the number in the number that it represents, and that will lead to a small change in the model output.
Understood. So this exactly is not scalable, but if you scale, maybe
Yeah.
more accuracy.
Maybe, maybe not.
Maybe, maybe
Yeah.
not. Okay.
So it's like it's just sorry.
Uh, Sorry, Lucas, did you have a question?
Yeah, just a quick one. Thanks for the cool talk. You talked about quantization, and I was wondering, tell me that doesn't make any sense, but could you quantize different parts of the model differently, or would you always quantize all the weights in the same way?
Great question. So you can do it differently. So for GPTQ, it do quantize for different layers. So it learns a different weight for different layers, but the way it learns the weight is the same, but it do that separately for each layer. So you can actually do have like some techniques that quantize the first few layers, and then other techniques for the second few layers. That's okay, but as far as I know, nobody do that. So, but you can do that.
I
You may.
have a separate question, but can I stack on to that? Are we just quantizing the weights, or are we doing it to like the token embeddings as well?
So it's only the weight.
It's only weights.
Yeah.
My question was, why do you like quantize a 32-bit model to make it smaller? Why can't you just train like a 4-bit model to begin with?
Great question. So as I just mentioned, so quantization is for post training. I mean, you already have the model, but it's from big tech, and you could not run it on your small GPUs. So what can you do? You do quantization. You compress the model for later use. You don't train the model again.
If it's so much cheaper for inference, wouldn't it make sense for big tech to train model? Like, there's a reason they're not doing it that way, right?
So 4-bit is less accurate. Like there is some gap between the 4-bit and the 32-bit, and they have the machine to do the 32-bit training. So why not?
It's very less accurate to the model, and when it's smaller quantized bits, basically you don't have the full information. It has cut down the information. So when you update gradients, you need to perform multiple calculations each time when you update gradients. They're getting multiple calculations that are adding on. So by the time the accuracy will be totally flawed by the end of the training.
I suppose for quantization layer training, you just need to keep optimizers to gradients. So I suppose weight quantizing.
It is, I think it's analogous to how JPEGs work. So you take photos using your camera, so it will be recorded in RAW. But if you want to just view the image, you use JPEG to quantize the whole image to some manageable size to store on your photos. But you don't take the photos in the small size.
Over here.
When I was trying to quantize my model, first you actually have to download the model, and then the quantization can sometimes take like overload your GPU, right? Because in order to quantize it, you have to have it in memory.
Yep.
Oftentimes, so it's like to reduce memory, you first have to have the GPU
Yeah.
on memory in the first place.
Yeah,
And it
yeah.
can take like hours to quantize as well.
Yeah,
How,
yeah.
how do you get around that if you can't afford like a really gigantic GPU? Because no, you have like when I use quantized models, I always use the ones that are pre-quantized because I can't do it myself.
Yeah, yeah, yeah. Good point. So,
Just like AI, quantize that
yeah.
quantize.
So you need to sacrifice something. If you don't have enough money, you need to either sacrifice the speed with runnability. So you can load the model using your small machine, but it can take a little bit long to run.
Saving money needs hard work.
Yeah, yeah.
Can you partition it and quantize each chunk? Or does that,
Yeah, yeah. I don't know much about that details, but I think it's possible.
Anyway, this is going to be applicable for training. So
All right,
getting
we
the
still have
data.
a little bit more time. We'll go here and then at the back. You first? Yeah.
Yeah, Tran, maybe.
Ooh, I'll need you to speak up. Sorry.
Okay. Actually, today we face a problem like if we have more than two models, one is level 2 and another is others. If we want to use it in a single GPU, do you have some suggestion?
So,
This is a problem we discussed in VC today.
so, so let me repeat the question. You asked about running two models on the same GPU.
Yeah, two models in one GPU. How
So
to making it faster?
faster.
Yeah, training faster.
To get
So you want to,
run them together, is it?
so
Yeah,
Or one by one?
together, and we can change the model.
so so there's something called GPU utilization. So like because uh, it's it's hard to say. So if you already utilize the whole 100% of your GPUs, there's no way to do more than that. But if like sometime like although the two models are running in parallel, but like one model is running, the other model is like resting. So so you can look at the memory GPU utilization in NVIDIA to see how much GPUs are being utilized when using the two models, and you can do some like very low-level engineering tricks to maximize those utilization. But it's a bit tricky to do. There's some library for you to do that. For example, the one is Zero is one of the way.
Do you think virtual GPUs or creating hypervisors over and above that could be an option?
Sorry.
Hypervising or creating virtual GPUs and creating over and above that could be an option?
So you want to make virtual GPUs? I don't think so because so if so you are faking the GPUs using.
A layer between them.
So you want to use, so if you fake in GPUs, you are using CPU to fake some RAM to GPUs, and so the CPUs already takes the training usually takes a lot of CPUs for moving the data around, and having the CPUs to fake in some GPUs, I think only slow the training time.
It will not fail. It will slow down further.
Yeah.
It will not fail.
All right, we got time for about one or two more. Up the back here.
Thank you, Dr. Isaac. So I remember from the BERT and Roberta era of like language models, they used to do this thing called distillation, where they will have a teacher and student model, and it seems like even then quantization was time consuming. So, like, how does this compare with distillation, or has it fallen out of fashion? Because I haven't seen that being done with GPUs.
So you want to compare between distillation and quantization.
Yeah, quantization and also LoRA, and how, because essentially they're doing lossy information
So distillation, so both are like for having smaller model using running on GPUs, but distillation take a whole different approach. So instead of changing the previous model, they want to have another model like smaller, but imitate the behavior of the bigger model. So to do that, they need to train the whole model again, and usually the time it need to take to train the smaller model usually take more times than LoRA. And so for a smaller model, so you need to collect the data, right? So you can do that by using like the bigger model to generate data to train, but so but it still takes a lot of time to collect the data.
Right. So this is like fine tuning versus
Training again, yeah,
reducing the size of the model.
yeah.
All right.
High one, high two, are they actually like a good teacher-student approach? Because in the past, it's for LLM and Tran.
Sorry, can you
Sorry,
please?
Like the high one, high two, like they use the hyperbolic data to train the model, right?
Yeah.
In that case, does it like get classified as student-teacher model?
Phi two, they as let me remember. So Phi two, they I don't remember, but oh no, Phi two use test you use Phi two use curated data, so they use data from books and all the high level source to train the model. Phi one I don't remember, but usually smaller model are trained by using like ChatGPT to generate the data. So like usually I do training vision language model, and having the vision, the image, the videos, and the text is difficult to achieve. So we usually have like some like image captioning model to generate the caption from in the image, and let ChatGPT generate the question answering using these captions. So so ChatGPT play a very important role in preparing the data for training. But I don't. But in Phi 2, I don't remember they doing that. You can have a look later. I might be wrong, but like. So distribution versus like test.
Yeah, distillation training. Like let's use probability distribution to create the loss, whether using something else like purely using text to text, but text from pseudo, text from p-sharps.
So yeah, there's two techniques, but I am not aware of any comparison. But I'm not working in distillation, but so I don't know whether which one is better. But recently, people are using like real labels instead of distribution.
All right. All right. One more, bro.